Inside every solar panel lies a silent, microscopic engine capable of the impossible, capturing a photon traveling at the speed of light and turning it into a flow of electrons. It is a masterpiece of material science, forged from one of the most common substances on Earth, sand. But to reach this level of efficiency, that sand must undergo a transformation so extreme it rivals the birth of a star. We aren't just building a gloss rectangle, we are engineering a semiconductor sandwich that operates on the laws of quantum physics. Every square inch of a modern panel is the result of decades of precision manufacturing, where tolerances are measured in nanometers, and the stakes are measured in gigawatts. To understand how we turn a beach into a power plant, we have to look past the blue surface and into the atomic structure of silicon, where the journey from raw earth to infinite energy begins. In this deep dive, we follow the life cycle of a solar panel, from the scorching heat of the arc furnace to the robotic precision of the stringing line, and finally, the torture tests that ensure it can survive 30 years under a relentless sun. It all starts with quartz sand, primarily silicon dioxide. But the sand on your local beach is far too contaminated for electronics. To create a solar cell, we need metallurgy-grade silicon. This process happens inside a submerged arc furnace, a massive industrial beast that reaches temperatures exceeding 3,500 degrees Fahrenheit. Here, raw carbon in the form of coal or wood chips is mixed with the quartz. The intense heat triggers a chemical reaction, stripping the oxygen away from the silicon. What remains is 99% pure silicon. But for the solar industry, 99% is effectively garbage. To be useful for electricity, we need solar-grade silicon, or 6/9 purity. That means 99.9999% pure. This is achieved through the Siemens process, where the silicon is converted into a gas, purified through distillation, and then redeposited onto ultra-pure silicon rods. The result is a silver metallic substance known as polysilicon, the bedrock of the renewable revolution. It is a process of refinement so intense it leaves only the purest atoms behind, ready for the next stage of crystalline growth. Now that we have ultra-pure polysilicon, we must turn these random chunks into a single, perfect crystal. This is the Kuzarkovsky process. The polysilicon is placed into a quartz crucible and melted in an inert argon atmosphere. A tiny seed crystal of silicon is dipped into the molten pool. As the seed is slowly rotated and pulled upward, the molten silicon freezes onto it, mimicking the seed's perfect atomic structure. This process can take over 48 hours of continuous vibration-free growth. The result is a massive single crystal cylinder called an ingot, weighing several hundred pounds and looking like a shimmering silver pillar. This monocrystalline structure is crucial because at the atomic level, grain boundaries act as roadblocks for electrons. By creating one continuous crystal lattice, we ensure the electrons have a frictionless highway to travel on once they are energized by the sun. The ingot is the diamond of the solar world, expensive, flawless, and the heart of high-efficiency energy production. The ingot is the diamond of the solar world, expensive, flawless, and the heart of high-efficiency energy production. The silicon ingot is a solid block of potential, but to catch sunlight, we need surface area. That means we have to slice it. Using a machine called a diamond wire saw, the ingot is cut into wafers thinner than a human hair, approximately 160 to 180 micrometers thick. Imagine a wire impregnated with industrial diamond dust moving at speeds of up to 50 miles per hour. This wire slices through the hard silicon with surgical precision, creating hundreds of wafers simultaneously from a single ingot. It is a delicate balance. Make the wafer too thick, and you waste precious silicon. Make it too thin, and it will shatter during the assembly process. Each slice represents a loss of material known as kerf, which is why diamond wire technology was such a game changer, reducing waste to almost zero. Once sliced, the wafers are cleaned in an acidic bath to remove any surface damage from the sawing process, leaving a perfectly smooth, mirror-like surface. These are the canvases upon which we will paint our electrical circuit. Pure silicon is actually a poor conductor. To make it generate electricity, we have to dope it with impurities. This is where the physics gets interesting. In a diffusion furnace, the wafers are exposed to phosphorus gas at high temperatures. The phosphorus atoms seep into the surface of the silicon. Because phosphorus has 5 electrons and silicon only has 4, this creates a layer with an excess of negative charge, known as the N-type layer. The base of the wafer is already doped with boron, which has only 3 electrons, creating a positive charge, or P-type layer. The boundary where these two layers meet is called the p-n junction. This is the heart of the solar cell. It creates a permanent internal electric field, like a hill that only lets electrons flow in one direction. When sunlight hits the cell, it knocks an electron loose. Without the p-n junction, that electron would just wander around and heat up the cell. But because of this engineered field, the electron is forced to move toward the surface, creating an electric current. We have effectively created a permanent physical battery that only needs light to activate. A raw silicon wafer is naturally shiny, which is a problem. If light reflects off the surface, it isn't being turned into electricity. To solve this, we use chemical etching to create a texturized surface. Under a microscope, the surface of the cell looks like a range of millions of tiny pyramids. When a photon hits these pyramids, it doesn't bounce away. It gets reflected downward into the cell, giving it multiple chances to be absorbed. Next, an anti-reflective coating of silicon nitride is applied using a process called plasma-enhanced chemical vapor deposition. This is what gives solar panels their iconic deep blue or black color. This coating is engineered to a specific thickness, exactly 1/4 of the wavelength of the incoming light, to ensure that the maximum amount of solar energy is trapped within the silicon. By the time we are done, the cell is absorbing over 96% of the sunlight that hits it. We are no longer just looking at a piece of silicon. It is now an optical trap designed to squeeze every possible electron out of the sun's rays.
We have mobilized the electrons, but now we need a way to collect them. We do this by printing a metallic grid onto the surface of the cell, a process called silkscreening. Using a silver paste, thin lines called fingers are printed across the surface. These fingers gather the wandering electrons and funnel them into larger bars called bus bars. There is a massive engineering trade-off here. If the fingers are too thick, they shade the silicon and block the sunlight. If they are too thin, they have too much electrical resistance. Modern multi-busbar technology uses extremely thin wires to minimize shading while maximizing conductivity. Once the silver is printed, the cells are fired in a furnace at high temperatures to sinter the metal, bonding it permanently to the silicon surface. On the back of the cell, a layer of aluminum is applied to create a back contact. The cell is now functionally complete, a single unit of power. But one cell only produces about 0.6 volts. To power a home, we need to bring these units together into a massive, unified array. To build a panel, we must connect 60 to 72 individual cells in a series. This is known as stringing. High-speed robots pick up the cells and solder them together using thin copper ribbons coated in tin. Because the cells are incredibly fragile, like thin glass crackers, the robots must move with extreme gentleness and precision. These strings are then laid out on a sheet of specialized, low-iron tempered glass. This glass is designed to be incredibly strong and highly transparent. Between the glass and the cells, we add a layer of ethylene vinyl acetate, or EVA. This is a clear, glue-like polymer that will act as a shock absorber and a moisture barrier. On the back, a durable backsheet is applied to protect the cells from the elements. This sandwich of glass, EVA, cells, and backsheet is then moved into a vacuum laminator. Under heat and pressure, the EVA melts and encapsulates the cells, creating a single, airtight, weatherproof unit. This is the moment a collection of parts becomes a finished solar module, built to stand the test of time. Before a panel leaves the factory, it must prove it can survive 30 years of the worst weather on Earth. This is the torture test. Panels are placed in climatic chambers where they are cycled from 40 degrees below zero to 185 degrees Fahrenheit, hundreds of times, to simulate decades of thermal expansion. Next comes the hail test. Pneumatic cannons fire 1-inch ice balls at the panel at speeds of over 50 miles per hour. The tempered glass must hold firm without cracking. We then perform an electroluminescence test. By running electricity backward through the panel, the cells glow in infrared. This reveals micro cracks invisible to the naked eye, cracks that could cause the panel to fail 10 years down the line. Finally, every panel is put under a solar simulator. A massive flash of light, tuned to the exact spectrum of the sun, triggers the panel. Sensors measure the output to the milliwatt, ensuring the panel meets its rated power. Only the perfect survive. Any panel with a defect is recycled, because out in the field, there is no room for error. The final step is the addition of the aluminum frame and the junction box. The frame provides the structural rigidity to withstand high winds and heavy snow loads, while the junction box on the back serves as the electrical interface. From a pile of sand to a high-tech energy generator, the journey is complete. When you see a solar farm, you are looking at millions of these engineered sandwiches, all working in perfect silence. No moving parts, no emissions, no fuel, just the elegant application of quantum physics. A single large-scale solar farm can generate enough power for 100,000 homes, offsetting millions of tons of carbon over its lifetime.
It is a testament to human ingenuity that we can take the most abundant material on the planet and the most abundant energy source in the solar system and marry them together to power our future. The age of the solar cell is here, and it all started with a simple grain of sand.
I hope this deep dive gave you a new perspective on the strategies and the relentless mindset behind these global icons. If you enjoy deconstructing business empires and tech legends in this Tech Archive style, make sure to hit that subscribe button and turn on all notifications. That way, you will never miss a new blueprint of history. For those of you ready to explore more boardroom coups and technological breakthroughs, I have handpicked 2 videos for you right here on the screen. Click one to keep watching. I will see you in the next one. Thanks for watching.